a goal of this here is our objective. And, oh, I wrote objective twice. Rate law is this, all right? That formula for any reaction, all right? Now we're gonna a mechanism. Remember, a mechanism is like all the elementary reactions that add up to the overall reaction. You could think of making a peanut butter and jelly sandwich is many different steps. It's not just this. All right, all right. So you get those. There's probably maybe you've got some other. You clean your knives before you do it. I don't know. I want to also talk about with these four steps for this mechanism of making jelly. For me, the slowest one is always the spreading of the peanut butter. Maybe it's because I like gob so much peanut butter on there, right? But the different steps themselves have different rates. And that's going to be important for this topic. Just like getting ready on a Monday morning, the one that takes the most, or maybe it's any morning, the one that takes the most time to me is getting out of bed. All right. It's the hardest thing to do. It takes the most time. Now, in each of these mechanisms, these two things are the slowest step. And therefore, we're going to call them the rate determining step. They're going to determine how fast the overall process happens. Uh, because they're the slowest step. All right. Now, this is a web like a graphic to show you all mechanisms have a rate. The rate itself is mainly determined by the slow step. If it's the first step, you just go by the stoichiometry. If it's a different step, we're gonna this is what we're gonna learn how to do, and these will be rate law like propose the rate laws, but you'd have to go back and look at experimental data and to see if it works, and your rate law should contain reactants only. All right, so we're gonna practice one. Here is a mechanism. All right, now you can see it's got two steps. All right, the first one is fast and the second one's slow. Therefore, we can't just go by the stoichiometry of the first reaction. We're going to have to do something with our with this slow step. The first thing you should do is I got ahead of myself. This is what's about. Those the double arrows, and that's what's written on top, and that's what's written on the bottom. Okay. Now you look at your first step, and you do the right laws, forward and back. All right. So that's the forward reaction, and that's the back reaction. Because this is at an equilibrium, you have both happening at the same time at equal rates, so they're going to be equal to each other. Now, here's my next thing. If you look, I want to solve this for the intermediate. Now, if you look at the reaction, what were my intermediates? Sorry. My intermediates here is something that got gobbled up, made and gobbled up. So something that got made and gobbled up was the intermediate. It's the NOB2. All right. So on the next step, I want to solve for that intermediate and then combine like terms as it says. So here's my intermediate. So to get it on its own, I want to divide both sides by k minus 1, and there's my equation solved for the intermediate. Now the third step is write the rate law for the slow step. And that, if you look, is the second step. And that's just going to be using stoichiometry. You're going to, here it's going to be rate is this because I've got one of each, so they're going to be first order, and then there's my constant, and that's going to go on the front. All right. Now the third step, the fourth step is to combine the two prior steps, basically, where I'm going to take my intermediate that I solved for, and I'm going to substitute in and make a rate law equation that lacks the intermediate. So I take this and I substitute it in. All right. and then I would simplify it. You'll notice that when I sub it in, I've got two NOs, and that means NO is going to be second order, BR is going to be first order, and I've got this big 3Ks here. You take these 3Ks and you put them together into this K prime or K apostrophe. And it's called the observed rate constant, and then you write your rate law. There it is. That's my answer right there. All right. Now, just to be clear, this K prime is that's what it is. It's all these other observed rate constants in the mechanism. And just to recap, a mechanism's got a rate. It's going to determined by the slow step. If it's just the first step one, you just do it's by the stoichiometry. You can write your rate law. If it's the second step, you got to do a little bit more. And I modeled doing this first one when I wrote the rate laws in the video above. You just go by the coefficients. And whatever rate law you get should have only reactants from the overall reaction and needs to be proven or supported by experimental data.